Hello everyone. So this is a recording of a presentation that was done at SOF 2025. So it was a presentation within the data analysis workshop, which I was lucky enough to co-chair with Sue Paring. So this presentation especially is on how to visualize the data, how to do graphs that are nice and well understood by your audience. So let's get into it. No disclaimers here. All right. Um, to start this presentation, I want you to think about the context in which graphs are needed and in which graphs are presented. So we include graphs in presentations, either oral or posters. We also use graphs sort of on a day-to-day basis. For example, when you do process quality control, you will also have some graphs in journal articles or in reports, and here the public is going to vary. It can be a very technical report that goes to your fellow scientists, or it can be a report that goes out to the public. But in any event, I think a common denominator here is that it goes fast, right? Especially if you think about presentations, you're going to see the graph on a slide for a few seconds, maybe a minute if you're lucky, and it's all going to go by very fast. Um, and so, yeah, what we want to do here is to make sure that the message we want to give with our graphs is being understood in the short time that it is seen. And so what we want in terms of graphs are graphs that are intentional, right, that are not misleading. We want graphs that are clear and that are concise. So throughout this presentation, I use different data sources to build some graph examples, and I'm going to be pointing out at the bottom of the slide the data source for you so that you can reach it if you want to. So surprisingly enough here, it's almost easier to start with what doesn't work in making graphs, because you can spend time talking about what does work, but it's really easier to just go by the counterexample and see why this isn't a good idea if you want to have a clear, concise graph that's well understood by the audience in a quick fashion. Okay, so first graph here, all right, you have this line chart. And if I ask you, quick, what are the opioids? Are the opioids here a big issue in this country? Really quickly. Are you able to do that? Probably not, right? Because you have to go, okay, wait, opioids. What in this list is an opioid? Oh, wait, okay, fentanyl, heroin, hydromorphine. Okay, so it's the yellow, the dark blue, and the lilac line. Wait, are these rising or are these falling? And then, so, it's a whole analysis process that you have to go through to get the answer to this question, right? Not very doable. And this is an instance of what we call overplotting. Okay, too many lines in this graph, too many information, and doesn't give me the clear picture of the question I'm asking. We have limited brain power, and what works best in this type of situation is to annotate your graphs to convey your message. So what you could do, for example, is to put something on the side that really carries out the message more efficiently. And so here I put, okay, stimulants, cocaine, and methamphetamine. And at the bottom, I have opioids, fentanyl, oxycodone, heroin, hydromorphone. And when it's annotated like that, instead of being a legend at the bottom, I see very quickly that stimulants are more of an issue in that country than opioids are in terms of number. Okay? You can also, another way to do that is to use facets to isolate. So facets are, instead of building one big graph with the lines, you do smaller tiny graphs, each with one line, like this. So you can go, oh, we have in our country more identification of stimulants than we have identification of opioids each year. And see here how I use the animation to deliver this message one step at a time so that it would be well understood, right? Instead of trying to analyze everything all at once, I deliver each part of the message individually. And another example of overplotting would be this, because I look at this and I go, okay, is there enough antemortem samples to draw a conclusion here? All of the points are on top of another. It doesn't tell me much about the number of points that are there. It's kind of hard to see. One way to ease that issue is to use what we call jitter. So jitter is going to spread out the points in the direction that's not quantitatively important. And so, of course, you don't want to jitter the points in the direction of the concentration, right? Because that's a value that we want it to be accurate. But if I jitter the points in that direction, I can still very well understand that what Venus, that all of these samples are Venus, which samples are cardiac, which samples are femoral. Very easy to understand because this is not a quantitative direction on the x-axis. And I can see more clearly the number of points that I have and their distribution in this way. Okay, pie charts. Let's look at pie charts. Tell me really quickly, can you rank the sections from biggest to smallest in each of these graphs? All right, so this is again one of those things that if I want to rank them, I need to spend a considerable amount of time, and it's not super clear either. Like, is B bigger than D, or is it smaller than D? Not obvious. Why? Because humans are bad at interpreting angles. Okay, so pie chart is not an efficient format to carry out information when you have several categories. You can use bar charts. Even better if the bar charts are ordered. Okay, here I've put instead of putting A through E in alphabetical order, I just ordered from biggest to smallest. And is it clear and obvious here which one is the biggest, which one is the smallest? It is 100% obvious in which order it goes. Okay. Another thing you can do instead of using pie charts is to use tree maps. Here's an example of a tree map. So we've seen this kind of graph a lot, especially in the MCDDA report, which is not UDA, but yeah, these are tree maps. So they're a good alternative to pie charts because we are better at interpreting areas than we are at interpreting angles. If you absolutely must use a pie chart, I would say label everything. First of all, I don't recommend it past 3 categories because as you can see here, it's kind of overwhelming to have more than 3 categories and have everything identified. It's a lot to take on. If you have 2 or 3 categories and you label everything, then I'm giving you a pass. But if you have a lot of categories and it's not labeled, no, absolutely not. Okay, next up on the list of bad stuff is 3D graphs. Why 3D? Why are 3D graphs bad? Again, they're hard to read. Okay, some values here seem to be above 100%, like in the regular, like the green bar in the regular category. It's probably not over 100%, and yet it seems like that visually. I get the general sense with this graph here that the activated is better, but it's hard to see the impact exactly for each analyte, like especially to compare, for example, the green bars, right? So anyways, hard to read, right? Are the activated vials useful for THC carboxy? Not sure. And this is an even worst example of 3D graphs. It's a complete mess because we don't even see the data for some of these drugs that are in the background, right? Bromazlam in the background, For some years, I don't even see the data. Same for heron. Okay, real mess here. Okay, I'm gonna have to admit that I did that purposefully, right? I could have put the bars the other way around, but I've seen some similar examples in conferences. So what do we do? Well, 3D graphs, they're hard to interpret, okay? The medium we have is 2D, okay? It's a presentation screen, it's a paper, poster that's printed. It's a 2D medium. So just stick to 2D graphs. Bar graphs, non-3D, are absolutely fine and much better, easier to interpret. And see here, I switched, instead of having two groups of columns that were regular and deactivated, I put the bars for each analyte side to side because that's actually what I want to interpret, right? I want to be able to compare each analyte side to side. Another option instead of bar graphs is to use facets. So again, I do these small graphs instead of having the 3D graph. And the worst of the worst of the worst is 3D pie charts. Because you're combining the difficulty to interpret an angle in a regular pie chart with the difficulty to interpret 3D figures together in one big beautiful mess. So there's like the only redeeming quality of this graph here is that everything is labeled, and so you can still read the data, right? But otherwise there is absolutely no reason to do that sort of graph. You can do instead an ordered and labeled bar graph, like this one here, right? Carries out exactly the same information, much easier to interpret. Um, so yeah, but I'm gonna say though, I say all of that stuff like I'm judging everyone who's doing different graphs. But this one was actually my own problem in my thesis that I did do a 3D pie chart. Fortunately, one of the examiners caught it, and I was able to modify it before the final version of my thesis went out. But it's just to say that this is hard learned stuff from from experience. So don't feel bad if you see my presentation and you go, oh, I did several of those things in past papers or presentation. I did those things too. All right, bar plots. What's wrong again with bar plots? Like, we're using them all the time in science. These bar charts with the error bars on it. Well, it's not that they're 100% wrong per se, but you need to be careful with them. Because if I ask you, hey, are these two groups the same? You look at the graph and go, yeah. I mean, the average is a bit different, but the error bars overlap. So yeah, they're the same. But the thing is that the bar graphs are going to hide the data between these descriptive statistics values, so the average and the standard deviation or the confidence interval. And if you dig a bit deeper, and for example, here you see the data with sort of a jitter that's applied to it and a violent shape that's attached to it. If I tell you, are both of these the same? Not really, right? I mean, you can see quite clearly that the distribution isn't the same in group 1 and group 2. So having a scatter plot like this, it doesn't hide the underlying distribution under the descriptive statistics. So that can be a bit better in some situation. It's not to say that you cannot do bar graphs, but you need to be aware that it can hide some stuff and check that this is not what you are doing with your bar graph. In any event, if you want to do a bar chart, you absolutely need to clearly explain what the error bars refer to. Okay, is the error bar one standard plus minus one standard deviation? Is it plus minus 95% confidence interval? Is it plus minus the standard error? I've seen all of that and some more. So it needs to be clearly spelled out in the legend what the error bar is referring to. Moreover, you should only be using those bar plots when the range of possible value is from 0 to whatever. Okay, if the only possible range of value is between 50 and 60, but then you draw a bar that goes from 0 to 52, like that doesn't make a whole lot of sense. Okay, so only use when the possible range of value is from 0 to something else. And the other caveat is you need to start the y-axis at 0. Why? Because otherwise it gives some weird sort of results, right? Oh, look at tiny Ariana here. Um, but of course that happens because the axis runs between 5 foot and 5'10", right? If they had started the axis at 0 as it should be, you wouldn't have this ridiculous outcome here. Maps. So maps are really nice. But look at this absolutely great comics from XKCD that says, oh, look at our site's users, subscribers to Martha Stewart Living, consumers of furry pornography. And the presenter says, business implications are clear. So what's the issue here? Well, the issue is that all of these are basically just populations map, right? They're basically identifying the large urban centers in the US. And if we dig deeper into this issue, here's what it looks like. I draw up a list of European countries and their death tolls per year. And I go, holy smokes, what happened in Germany? Like, why are people dying so much in that country? What's going on? But of course, it's just because the population is bigger in Germany. And so, yeah, they have more people dying. And the lesson here is that population inevitably drives the frequency up of whatever you are measuring. You know, there might be a few exceptions, but generally speaking, that's what happens. So what's the solution here? Well, you always need to ratio to population. So if instead of looking at just the deaths, I look at the proportion, I look at the mortality rate by 100,000 inhabitants, then I go, oh, okay, this is a lot more stable throughout the different European countries. There still are some differences, mind you, but this is not from, you don't have 10 times the death rate in Germany than you have in Belgium here. They're different, but they're not 10 times different. So always, 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 always ratio to population. And this is one I see so often in conferences like SOFT and TIAFT. Misleading data visualization. As I said at the beginning, right, a good way to learn is by looking at poor examples, and this is what we've been doing up to date in this section, right? Going through some bad examples one after another, or bad practices one after another. But really, a good way to learn is just by looking at one poor example after another, and then you start to pick up on like what the different issues are and how to do it better, because yeah, you look at that and you go, oh, that's not so good, and you also think about how you would improve it. So here are in this spirit a couple of websites that contain bad data visualizations that you might want to look through when you're bored. And here are a couple of examples that come from these websites. Right, this one here is a poor data visualization example because the double y-axes are always risky, right? So here you have the Netflix stock from June 2011 to 2013, and then Tesla from January 2019 to today. So first of all, The two periods are different, but then the axes are different as well, right? Um, and so this is the risk of identifying a spurious correlation when there is none, actually. Another risky practice, not starting the bars at zero, and that's something we've seen with the height of the different pop singers. But if you look at this, for example, and you go, oh, wait, BZE is horribly imprecise here. It's so far away from the target concentration. But if you read the axis, you're like, it's 15 nanograms per ml off of a 500 target. It's actually not really bad. Right, but that's because the axis starts at something other than zero that you get this false impression. Another risk is a having some broken axes, and I understand that sometimes it is needed because you have some tiny values and some very big values, and you can't really fit all of that in the way that's readable in a single graph. But it is risky because the lent is the encoding mode for a graph like this, and by chopping the axis, you're messing with the encoding mode. So it's easy to distort things. So what this is showing you here, is that if you want to break the axis, then what you should do is break it as close as possible to the top of the first bar that is of a bigger value or bigger intensity, and not cut it lower down where you get the misleading impression of, greater height. Okay, so we've gone through a lot of what does. So what works then? Well, again, we go back to this idea that graphs need to be intentional, right? They shouldn't be misleading. They need to be honest. They need to be intentional. They need to be clear, and they need to be concise. So you're going to need to really think before you do your graph, before you plot. Think about, what is it that I want to show? What is the simplest way to show it to my audience? How can I make the main message obvious to my audience? Nobody knows the data and the story like you do. And we often think, as a scientist, I should let the data speak for itself, but that's not realistic. You're giving like a 10-15 minutes presentation. You cannot put all of the data out there and expect the audience to get away with your take-home message if you didn't do some of this work for them. Okay? You're the subject expert. The full data set, it belongs in the supplemental data of the paper. It doesn't belong on the slide in a conference presentation. Okay? What you're going to want to do is really reduce the cognitive load for the audience. Okay? Make some of the work for them, make the message obvious, remove what's not necessary, and really make clear what your main message is. Be minimalist. If it's not relevant to your message, it has no business being on the slide, being on the graph. You want to keep backgrounds element in the background. If you have grid lines, but they're too dark, or whatever is in the background that overpowers your graphic and your main message, that's not helping anybody, because the brain of your audience is going to be busy analyzing those elements instead of focusing on what the main issue here is. Order your bars. Such an easy step to do. Really helps with interpretation instead of going back and forth between the different bars. Makes a lot of difference in terms of interpretation and ease to read the graph. Annotate your graphs. Again, by far the easiest way to convey your message clearly, annotate your graphs and be consistent with color, with shapes. Couple of illustrations of what I just said. Right, here's a bar graph. Bars are ordered in alphabetical order. Clearly not a lot of thought put into this. If I want to interpret this graph, I'm seeing this graph in a presentation and I want to know, okay, what are the biggest issues here, the biggest offenders, and I need to go, ooh, okay, methamphetamine, and then, okay, carboxy THC, and then, okay, that's cocaine, and then, oh, GHB, interesting, GHB is up on the list. Quite a lot of work that I need to do to get there. Instead, what I have this. Oh, okay. Well, that's much easier to read, right? I have all of my substances here. Boom, boom, boom. Methamphetamine, THC, carboxy, cocaine, GHB. Oh, GHB. And what I can do is even have animations and annotations that come up in a presentation. So for example, if I were to present this graph, I could say, so here is a graph of the top 10 substances that we find in the RE cases. And as you can see, GHB accounts for 24% of all of our cases. Okay, so you see how I present the full graph and then I add an annotation that makes my main message very clear. And by the way, yes, that's real data from a few years back in our lab. So we have a lot of GHB in, or we used to have a lot of GHB in our DUI cases. Okay, be consistent. Be consistent. Let's say I have this graph up in a presentation. Here are the number of samples analyzed by Health Canada that had fentanyl and methamphetamine in it. And then blah, blah, blah. I talk about that. You can see it's increasing year over year, blah, blah. And I go to the next slide. And then I go, see how the trend, the growth in sample is, blah, blah, blah. But then see what I did? Fentanyl is red here. Fentanyl is blue here. Okay, so from one slide to the next, I just switched my color scheme. Okay. And your audience was like, oh, okay, red is fentanyl. And then, yeah, I'm listening. And then you go to the next slide and suddenly it's the opposite color scheme. So that is a recipe to be misunderstood. And you might think that this is sort of an obvious thing, but I've seen it several times in conferences. So be consistent in your color scheme. Pay attention to details. They're important in terms of graphs. The font size, okay? The number of times I've seen in conference presentations or in papers, font sizes that are unreadable, maybe because you've just screenshot the MSMS graph and put it in your presentation without modifying the font size. Um, well, you might tell me, okay, but what happens if I can't fix the font size, right? Maybe I have a chromatogram in my data analysis software, but there is no way for me to make the font bigger in that data analysis software, to make the lines bolder. What do I do then? Well, one option is always to use PowerPoint to fix it, right? So you can do your screenshot, put it in PowerPoint, and then on top of the small font size axes, you can lay another axis in PowerPoint with the labels that are bigger. So yeah, it's work. It is work. But details matter if you want your audience to understand what you're saying. So you can use PowerPoint to sort of build on top of it and fix it. Another option is to just recreate your plot. And one way to do that is to use the online website Plot Digitizer. So basically you can import a plot and you have a few parameters to put in, and it's going to spit out the data that's underlying that plot. So you can use that data and go back to, for example, Excel and recreate a full graph now with, the proper font size and blah, blah, blah. So Plot Digitizer, really nice tool. Another detail, use sans serif fonts. So serif fonts have these little tiny thingies at the bottom and at the top. And this might not matter to you, but for some people, it makes the fonts a lot harder to read, right? And so in sans serif fonts, you don't have the little thingies at the bottom, it's straight lines. They're much easier for the brain to process. Again, not for everyone, but for some people. So, easy thing to fix is to just not use sans serif fonts. Use colorblind friendly palettes. And this is an easy one to miss, right? But if you put some green and red, which is, the typical error that we tend to do in terms of colorblind, then look at how it looks for a colorblind person. There are 3 different types of colorblindness, right? And look at how these look similar for a colorblind person. And yeah, I'm always going to remember one of my colleagues who was colorblind, and in the analyst software from SciEx, which isn't used anymore, but in the analyst software from SciEx, green and red were the first 2 basic colors that were used in chromatographs and in trend lines. And we had several meetings where he would identify, like, look at this green line, and we'd be all like, no, it's a red line. But it was extremely confusing for him, right? So easy thing to fix, and I put a link here, but basically you have websites where you can input your RGB codes for your colors, and it's going to give you these palettes here, so you can check if these look similar for colorblind people. And sometimes it's quite surprising, right? So this green and this blue look quite similar for this kind of colorblind person. They're really similar one to the other. So anyways, yeah. Okay, just want to give you some resources that you can go to if you want to learn more about this. So Data2Viz is such a beautiful website. It really is amazing. So I'm gonna say you might want to go there just to learn about stuff, but it is really more of a tool that's helpful when you want to do. So when you want to do some graphs, you use that as a companion, because basically what it does is it guides you through the process of building a graph. It asks you, what type of data do you have? Is it, categorical, one categorical variable, one quantitative variables, or do you have 2 quantitative variables? And then it tells you which type of graphs are available for this type of data. Then when you click on this, then it tells you what the pitfalls are with this type of graph that you must pay attention to when you build your graph. It is an incredible resource. Okay, nothing like a good book, right? How Chart Lies by Alberto Cairo. Very, I'm going to say, yeah, whatever your level, it's quite a basic introduction to how graphs are made and what you need to pay attention to. And yeah, you might think that as a scientist, you've seen quite enough graphs in your life that this isn't really useful to you. But there's always something to pick up. And also, I'm going to say just spending some time thinking about these issues, even if you don't yeah, even if the stuff in there doesn't blow your mind, just the fact that you're going to spend an entire book thinking about building graphs and how to properly represent information is actually worthwhile on its own. So very good introduction for everyone. Storytelling with data, storytelling for you. Excellent books, excellent books. And they're really focused on how to build data visualization for a presentation for a specific audience. And yeah, they're really just a summary of tips to help you get your message across. Really good books. The Art of Data Science is more of an advanced book, and it's not only on data visualization. Far from that, it's on the whole process of gathering data, asking questions, refining the questions, all of these cycles we go through when we analyze data for a stakeholder. So good reference, really, if you want to go further in. You leave this workshop enthusiastic about deepening your data analysis practice, this is a good book to go through. This is online, a bit of a more technical essay on what are some good and bad data practices in visualization, and you have lots of examples, so that's nice. Uses maybe a bit more technical vocabulary, but still very readable. And why not an Instagram account, Chartosaur, that I discovered quite recently that makes small videos about different pitfalls that you can have in data visualization. So very, very nice, very quick and snappy account. Yeah, always good to go through your feed of like pictures and then suddenly you have something on data visualization. Okay, so if you have any questions, comments, please don't hesitate to reach out by email or on the different social media platforms. I'll be happy to hear from you. And I'll be happy to, I look forward to your different data visualizations.